Let me start out by a pretty easy example. So that you can actually predict what's happening before we do the computation. So what I want you to think about is this function fx comma y equals to x on this interval 0, 1 times 0, 1. Now I have to explain what this means. This times means it's a product set, but since a lot of you didn't learn what product set is, let me just explain it to you the following way. On the xy plane, 0, 1, the first one is for 0, 1. 0 to 1 is this interval here, right? And 0 to 1, the second one is for the y. On the y-axis, 0 to 1 is this interval. And the product set of these two means it's just this square formed by those two. Okay, so for example, if this was like 1 to 2 and this was like negative 1 to 0, if it's 1 to 2 and negative 1 to 0, you're going to get a square here. So that's what the product set is. Okay. Now, imagine the graph of this function, z equals to f of x comma y. What kind of graph is this? It's z equals to f x y requires the z-axis, right? And because fxy is equal to x, we're really trying to draw the graph of z equal to x. And recall that if all of these variables are of the first order, in three-dimensional space, this gives you a plane, right? It's a graph of a plane. And I hope you will be able to see what kind of plane this is. So let me give you a multiple choice question. Is this z equal to x a plane that's slanted like that, or maybe this one? The first one is you have just two choices. Is it this one or that one? Can you imagine?
Yeah.
What makes you think that?
Because z, it says x equals z, so it should have a.
I think it's the second one.
I think it's the first one.
Second one, because
The
the
second
second,
one,
because
because
it has
it
to
has
fit
to
into
fit
the
the
limits.
0, 1, 1, 0.
All right. Now, if in doubt, and you want to think about a graph in three-dimensional space, what do you do? You use level curves. Yeah? No? Level curves. Is that something new? You've never heard about level curves? All right, level curves. So you have, what are the level curves here? If you said z equal to 0, what's a z equal to 0 level curve? This entire thing is z equal to 0, right? What's z equal to 1?
1.
Is it a horizontal line or a vertical line? It's a vertical line. Z equal to 2. Okay, so what kind of plane is it? Is it this one or that one? First one or the second one? It's the first one, of course, because you can see that here the levels are same, and then here this is the same level, that's the same level. Just going like that. Okay? Got it? Okay. Wow, that was much harder than I expected. See, a lot of you just don't think before you answer. You should think. It's not that hard. Right? It's equal to 0, 1, 2, 3. You can just see it. All right, now, if you have this kind of plane, what's the shape captured over this domain? What do you think? It's a three-dimensional object, right? So if you had this plane and you only cut it, you took a knife and cut the portion above this region, below this plane, what kind of shape would you get?
Triangle?
It'll be a three-dimensional object with one side being a triangle. But there are some rectangles too, right?
Yeah.
Or squares too, right? It'll be this one. Okay? What's this length?
1.
1. What's this length?
1.
1. What's this length? 1. What's this length? 1. Okay. What's the volume? What? What's the volume? Say it louder. I think somebody said it. What's the volume?
1.
No. Why are you saying 1? I said it's not. It's not 1. What's the volume? 1/2. How do you know it's 1/2? Who said it? You said, okay. How do you know it's 1/2?
Triangle. More because.
Okay. Well, you can go by that. Yeah. Triangle and then what? Yes.
If you had it as a cube, if you had two sides to it, you're cutting it off, so that would be 1 times 1 times 1, so it's just half of that.
See, this is half of a cube, isn't it? Right? And what's the volume of that cube? Base times width times height, which is 1. This is half of it. So it's 1/2. The volume is 1/2. Right. The volume is 1/2. Okay. All right. Now, related to this, let me show you something new. I want to do f(x, y) dx dy. This is a multivariable integral. It's an integral of multivariable functions. And because we have two functions, I can integrate by x, and then I can integrate by y. So multivariable functions, because it has two variables, you can integrate not just by one variable. Of course, you can just do it by one variable, but you can also integrate by the next. Okay. And then I'm going to put for x varies from 0 to 1, right? X goes from 0 to 1, and y goes from 0 to 1. All right, before I actually do the computation, let me explain what this means. First, dx times dy. Now, what is that? Dx is a very small increment in the x direction, and dy is a very small increment in the y direction. So when you have dx times dy, you basically have a very small square, or a rectangle, very small rectangle, with these base and height being infinitesimally small. It's like very, very small. It's like smaller than a dot. Okay? And over it, you have this function. See, over it you have this function. Right? The function is like this in our example. So dx times dy is a very small piece of this land, and over it you have some function. And then when you multiply the value of the function, because the function value is the height, you know that function values are the same as the height. That's true even in three-dimensional space. So if you have x and y and z, then if you have a two-dimensional function, at any point x, y, the value of the function is represented by the height of the function. Does that make sense? Height? So what you have is some kind of height multiplied to this base area. And if you have height times the base area, what do you get? you get the volume of this column, right? And that's very, very similar to what we did in 2 dimensions, in one variable case, in calculus 2. In calculus 2, what did we do? If we had a function and we had an interval a to b, we cut this into very, very small sizes and said this length is dx and this height is f of x. And if you multiply f of x and multiply by dx, you get the length of this rectangle, right? You get the volume of this, area of this rectangle. You get the area of this rectangle. And then how do you get the area of the entire thing? You add them up. That was the idea of integration in one variable case, right? And the integral, the definite integral of f of x dx from a to b represented the area under the curve, right? We're playing the exact same game here. The only difference is now, instead of having an interval downstairs, you have some kind of a domain, a region, in the x and y plane. Okay? And over it, you have some function. And if you integrate the function with respect to dx and dy, this area times height, you get the columns, and you're adding them everywhere, adding them over this domain. So what would that represent? What meaning would this have?
Volume.
It would be the volume of, volume under the graph, or actually, let's say, surface, because we learned that z equal to fx comma y, this is a surface, right? It's a volume under the surface. If you have certain surface, then that integral gives you the volume under the surface. So the volume under the surface is obtained by doing this definite integral. Okay? Now let me demonstrate that this does give us what we think it should give by doing the exact calculation. We know the answer already, so if we get the same answer doing that computation, then we can be confident that it is really what we think it is. Okay? So fx comma y for us is just x itself, dx dy. So let's compute this. What's x integrated by x?
1.
Integral of x is 1/2 x squared, right? And then you have to plug in 1 and 0. And if you plug in 1 and if you plug in 0 and you subtract, what do you get? What are you getting? 1/2 of 1 squared minus 1/2 of 0 squared dy. So you're getting integral of 1/2 dy. Now what's the integral of 1/2 by dy? 1/2 y. Right? And then here you're plugging in 1 and 0 and 1 and 0. So you get 1/2 of 1 minus 1/2 of 0. So it's 1/2. Exactly how we thought it should be. Okay? Good?